Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So in this part, we see how you want to design a FET common source based on the frequency response. So this one is the circuit which we obtained from our first chapter here. Okay, so we have this one is the fixed bias. This one is the self bias, and then um, okay, this one is the self bias, and this is the um, design the amplifier. Okay, for the self bias, and as we know that for the voltage divider bias, the method is same for with the self bias, but the only difference is either to determine the value of R1 and R2. Okay, so we apply the same step to determine for the frequency response. So we are using basically a same circuit, but only we add two resistor R1 and also R2 as a voltage divider bias. So this one is the this is the specification where we need to obtain, where our Z out should be greater than 1 kilo ohm, Z in should be around 1 mega ohm, RL we set at the 100 kilo ohm, AV so we need more than 10 dB or 3.16. VCC we set between 10 to 20 volt, and this is the for the VO max. And we add another two specification, which is for the low and also the high cutoff frequency, which is we need to obtain around 100 hertz for the low cutoff frequency, and for the high cutoff frequency it's around 100 kilohertz. Okay, so this one is same from our previous chapter, which is we are using same transistor, which is 2N5556. This one 2N556, and this is the how you want to obtain value of VJS off or VP, and also the IDSS, which is zero gate voltage drain current. Okay, so we take the middle point. So we have the in here, so we have the minimum and so the maximum value. So we take the middle point of the value. So we can obtain the value of IDSS around 1.5 milliampere, and for the pitch of voltage VP is around negative 2.1 volt. Okay, so the first part is we need to this one is from our previous slide from the chapter 1. So this is the value of resistor which is we obtain here. So we get all the DC parameter, and here, so for the first part we need to add one component, which is the R signal resistor. So in order to determine the R signal resistor, so we need to determine the value of Z in. So Z in is come from our input voltage. So we need to draw, basically we need to draw the AC equivalent circuit for the common source. So basically the circuit is like this. Okay, so we have R1 paired with R2, and we have gate here, and we have the like this. Okay, you see here we have the R1, R2, we have the common source, and we have the RD. Okay. So this one is the gate, this one is our drain. Okay, this one is our source. So we have the current here, GM VGS, and this one is our RD. So this is our VO. So Z in is in this part. So this is our Z in. So basically Z in is the R1 parallel with our R2. So we have around 3.14 mega ohm, and then so this one basically we want to determine the value of RS. So the ratio, so we have here let's say, sorry, this one should be VS. Okay, this one is our VN, VIN. Okay, we do the voltage divider. So we see these two resistor, RS and also our input impedance Z in is in series. So So in order to determine the value of V in, so we do the voltage divider method. So V in is equal to Z in time our resource from our function generator. So what we need to do is we need to set this ratio is around equal to 1. Okay, so in order to get our value, this ratio nearest to the value of 1, so we need to make sure our RS value should be less than our Zin. So the method that we can apply here is we can divide our once we obtain the value of Zin 3.1 from mega ohm, so we can divide with the 100 or 10, something like this. So we can get around value around 1.4 kilo ohm. Let's say I set around 100, so we just divide our Zin value with the 100, and we got our RS signal. And then we determine the value of GM. So this one is the IDSS, and we obtain from the datasheet. VP same, and this one is our VJS and also the VP VJS, which is we obtain from our previous chapter 1. Then we get the value of GM. Yeah. Okay, so we already so this part is how you want to determine the value of R signal here. And then this same method from this one is same specification from our chapter 1. And for the frequency response, for the low cutoff and also high cutoff frequency. So basically for the low cutoff frequency, we need to determine the value of capacitor, right? Capacitor. So basically okay, so we need to know what is the value of capacitor at the gate. Kita kena tahu lah what's the gate capacitor here in order to determine to get when we set the low cutoff frequency, right? So like this, so if you see, we have the Z in C in, C out, and CS. So we have three for the low cutoff frequency, we have three frequency like this. So this one is the bandwidth. Okay, so we have around like this. The highest point either these three capacitor, okay, is the effective low cutoff frequency. For our case, we set the effective low cutoff frequency is around 100 Hz. So it should be here 100 Hz, and the rest should be less than 100 Hz. So maybe we set around both of these two capacitor, maybe around 10 Hz. Okay, so since we obtain the value of capacitor, the value of frequency here, so by using the formula, so we can this formula, so we can easily to get the value of capacitor. So the effective low cutoff frequency we set at the source, so the rest of the frequency we set at the input and also at the output. Yeah. So this part we set around 10 Hz. So this one we set around 10 Hz, and this part we set around 100 Hz. Okay. So at the gate, so we need, in order to determine, so this one is the formula how you want to determine value of capacitor at the input. So we need to know the frequency, the low cutoff frequency. So we just divide with our effective frequency 100 Hz with 10, so we get the 100 Hz, and we need to determine the value of input impedance at the gate. So input impedance at the gate, we just remove our capacitor here. So this one is our capacitor C in. So we remove this capacitor, and we see what is the input. Let's say we set a name as ZG. So we need to determine what's the value of ZG at the input. Okay, so if we see here, we have two resistors in parallel and series with our R signal here. Okay. these two resistors in series. So this one is parallel, and these two resistors is parallel, and we add with our R signal. Okay, so this one is in series, so we get the ZG is around 3.1 mega ohm, and okay, so this one is mega ohm. Okay. So our capacitor value should be 2 times pi times 10 3 point. So firstly we check first, maybe something like mega ohm parallel with 4.475 mega ohm, then we add with 81.4 kilo, so we get 7 mega ohm. Okay, so 2 times, so this one is not correct, times 10, 7 mega ohm. So this one is so this one only the typo, so the value is correct. We get around 5 nanofarad. So the next step we determine the capacitor at the source, the source. So this one is basically we have capacitor here, and so we remove the capacitor. This capacitor we remove, and we need to determine the total resistor at the source. So we name as a ZS or ZX. So for this case we set the ZX, so we need to know what's the value of ZX, and then we do the KCL, Kirchhoff current law. Okay, so we name this network IX, this one is IRS, this one is the GMVGS. So from this point, okay, this node, so this is the KCL equation. Okay, so uh, so to get the value of Zx, so we apply the KCL, and our should be our final equation here. Zx, as we know, the Zx it should be Vx over Ix. So this is the KCL equation. So Ix equal to Vx over Rs, and we have the negative Gm Vg minus Vs. So we know that when we want to determine the value of Zx, so we need to short our source. So basically our source becomes 0 lah. When we short this one, it becomes 0. So from our equation, so we have Gm, so we have Vg, so Vg becomes 0. So we have the negative Vs, and negative Vs is should same. This one Vs is equal to our Vx. So negative. So this is our Vx here. So Vx is equal to Vs. So we have the negative multiple with the negative, so we get positive. So we have the final value is Vx divided with the Ix equal to Zx, and we have the Rs parallel with our 1 over Gm here. Okay, so if you see here, if you extend our equation here, so Vx, so we have the Vx over Rs plus Gm over Vx, so Vx 1 over Rs plus Gm, then so we have Vx over Ix equal to 1 over Rs plus Gm. So this equation basically equal to the two resistor in parallel, R1 and R2. So when we have these two resistor in parallel, so it become 1 over R1 plus 1 over R2, like this. So this equation similar with this equation. So we can rewrite our this equation become Rs. So this one become R1 parallel with the R2. So it become Rs parallel with 1 over Gm, like this. Then we get the value of Zx equal to 807.71 ohm. Then we can apply the equation. So we get the capacitor at the source around 1.97 microfarad. So at the output, so we only have okay, at the output. So when we short our source, so this one become open. So we only have only one resistor, which is the RD, and this one is our C out. So we have the Z out is equal to RD, and same since we set all the capacitor here at the input and so the output around 10 hertz. So uh, we get the value of capacitor at the output 5.51 microfarad. Okay, so we applied from the datasheet for this transistor. Okay, we have three AC parameter, which is the input capacitance, reservoir transfer capacitance, and output capacitance. And then we apply this formula lah, in order to determine the value of CGS is equal to CIS minus CRS. CGD equal to CRS, and CDS equal to COS minus with our CRSS. And then so we draw our SC model for this FET transistor, and then we enable all these three capacitor, all these capacitor. So if you see, we have the common source here, this one is the common source, and so basically this one we grounded. So we have the one capacitor which is connected our input and also our output, which is CGD. CGD. CGD ni akan jadi kita punya capacitor yang akan menghubungkan between input and so output. And we have another two capacitor, CGS and CDS, which is connected from our input to the ground, and CDS output to the ground. Okay, so this capacitor we need to transfer by using the Miller concept like this. So we name this one C Miller in, another capacitor here C Miller out. Okay, so we apply this method. This one, so we have the capacitor here, then we convert here to the input and to the output like this. So it become ZF Miller in, ZF Miller out. Then we can determine capacitor C Miller out and capacitor C Miller in. So our case CF in is equal to C GD, if I'm not wrong, C C gate to drain, CGD. Okay. So we apply this formula to determine so we have the CGD, our capacitor Miller, then we can easily determine the capacitor at the input side and capacitor at the output side. So at the capacitor Miller in, so we have CGD. When we apply the we need to firstly we need to determine the AV, which is we obtained from our first chapter. So this one is the 3.10. So we put exactly 3.10 exactly here. Then and we add with our, so as we know, we have two capacitor in parallel, CGS and C Miller in this capacitor. Okay, so when we have two capacitor in parallel, so the operation is add. We just add here. Okay. So this one we apply the concept of Miller, and we have the C Miller in total, C Miller in total 8.1 picofarad, and then we need to draw the IC equivalent circuit um, for the high frequency response. Okay, so basically become like this lah. So we have resource, this one is R signal, then we have R1 parallel with R2, then we have one capacitor here, C Miller in. Okay, then we have here, we have the RD. Okay, so we have here RD parallel with our RL, and this one is similar out. So this one gate, drain, and this one is our source. Become like this. Okay, so to determine R is in, so we remove this capacitor. So we apply the same concept which is we apply at the low cut frequency. So we remove this capacitor, and we find out what is the total R is in here. So we short our source, then you got R signal parallel with R1, R2. So this one is a total resistance at the input, and then we determine the value of frequency, then we get around 632. Same thing we apply at the output. So this one we apply the capacitor Miller output, we get around 4.97 picofarad, and we remove the capacitor, and we find out what is the RH out total. So we have the RP parallel with our RL. When we remove the capacitor, we show our source, and this current will be open, and we have only one resistor, and then we determine the high cutoff frequency at the output side. So we get the final value is 11.4 megahertz. If you draw the bandwidth, okay, our frequency response. So basically this is the frequency low. So from our design, we know that we set the capacitor. We have 3 capacitor at the input and also at the output. For the low cut frequency we set around 10 hertz like this, and this one we set around 100 hertz. And for the high cut frequency, so we have two value of frequency here. So the effective high cut frequency is the lowest one between these two capacitor, between these two frequency. So the lowest one is 632. But in our specification, we need to set around 100 kilohertz. So in order to obtain 100 kilohertz, what we need to do is, okay, this one frequency high, we need to set 100 kilohertz. Okay, so what we need to do is we need to add okay, this one. So we need to add one capacitor, one capacitor we name as a tuning capacitor CT at the. So in this case we choose either input or output. For this case we choose at the output. So we set our high cut frequency at the 100 kilohertz. Okay, and then we determine, we apply the formula. Okay, same formula, but we choose what is the capacitor value which is we need to add in order to get the value of high cut frequency at the 100 kilohertz. So the output capacitor should be 566 picofarad. And then at the output, so we have the total capacitor which is 4.97 picofarad. Okay, so what we do is, so we know that the total capacitor is CT plus C Miller out. So mixing C Miller out is 4.94 picofarad, and total capacitor at the input side is around 560 picofarad, and then we can get the tuning capacitor 561 picofarad. So these two capacitor, this CT capacitor, so we apply at the this one we apply at the output side. So at the output side, when we add this CT with our similar up, then we get around 560 picofarad, which is this capacitor will affect our high cut frequency at around 100 kilohertz. Okay, so we draw this all the circuit by using the LT spice. Okay, so we have this one, common source, FET common source. So we take this circuit. Okay, so we just add okay, so this one, the circuit. Okay, so we have 10 megahertz. Okay, 10, oh sorry, this one, 10.52 megahertz, mega ohm, 4.47 for the R2, and for the RT we have 2.89 kilo ohm. This one 5595 kilo ohm. At the C-in we have 5 nanofarad, CS 1.9 microfarad, 1.5. So this one. So we check dekat source kita set 1.97. So we just double check first. 1 kali dengan 100 kali dengan 2 kali dengan pi, 1.97 microfarad. So 1.97 microfarad. Okay, CT 561. Okay, CT 561.45 picofarad. Okay, kemudian CO C-in CO 5.51 microfarad. 5.51 microfarad. Okay, RD 2.89K 2.89K 2.95K 4.475K. Ini dah betul dah, betul dah. BSS 15 volt 100. Okay, so lebih kurang semua betul dah. Alright, so we run the circuit. So at trace VO in. Okay, so kita dapat kat sini. So we set to the phase. Kita bawa ni ke 180 lah. So ini kena bagi dekat dengan 180. Okay, like this. Okay, tekan ini. So kita akan dapat gain dia. Kita set kepada 5 ni, dapat lebih sikit lah, 7.3 tak apa. Okay, so kita dapat ni 7.36 dB. So kita minus dengan 3, so dapat 4.3 lah, 4.3. So kita buat kat sini 4. Oh sorry, kat sini decibel. 17. So kita tolak dengan 3 dapat 14. 14.3 14.3 14.3. Ni lari sikit. Tak apalah. Kita buat dulu. Dah lari sikit kat sini capacitor value kita. Kemudian sama juga kat sini kita boleh dapat high cut frequency 14. Okey, lebih kurang kat sini lah. So kita dapat frekuensi untuk low cut frequency, kita tak berapa exactly dapat. Kita set kepada 100 kHz, dapat dalam 200 Hz. Tapi untuk high cut frequency kita dapat dalam 100 kHz, exactly 100 kHz. So this is how you want to design for the high cut frequency. Okay, for the common source. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.